Hey there. So previously on this channel we have looked at the directional derivative of a two variable function and the kth derivative of a single variable function, and we found out that this equals this and this equals this, and today we are going to be looking at a hybrid of these two, which is the kth directional derivative of a two variable function. And this is going to be a fun ride, and the formula for this is actually a sort of hybrid of this formula and this formula, and you'll see what I mean. We want to find the kth directional derivative of f of xy, but first we need to look at what does this even mean. So for example, if you have the special case for k equals 2, then what I mean by this is that this is just equal to the directional derivative of the directional derivative of f of xy. So this is just using the Leibniz notation. I've put 2 in the exponent, and in general you can say that if you have the kth directional derivative of f of xy, we are talking about the directional derivative of the directional derivative of dot 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 directional derivative f of xy with k iterations of the directional derivative. So this is what it means, just like the kth derivative of a single variable function. And using this definition, we are going to be deriving a formula for it. So before we get to the generic case, let's do the second directional derivative, because doing special cases may show us a certain pattern like it did in the kth derivative of a single variable function. So let's do the second directional derivative and let's see if we can notice a pattern. And we want to take the directional derivative of the directional derivative. So basically we are taking the directional derivative like this on both sides, and it will look something like this, just cos theta times the directional derivative of f sub x, which is the partial derivative of f with respect to x, plus sine theta times the directional derivative of f sub y of f of xy. So this is what we want to calculate ultimately. And how do we do this? Well, here we have f sub x of f of x of xy. So basically f sub x is also some arbitrary two variable function, so we can just plug in f sub x over here. So you will have cos theta times, so now you'll have f sub x differentiated with respect to xy, and that times cos theta, plus f sub x differentiated with respect to y times sine theta, plus now this part, so you'll have sine theta times f sub y differentiated with respect to x. So you'll have this xy times cos theta plus f sub y differentiated with respect to y, so you'll have y. And this is what you get ultimately. And now if we simplify a bit, first of all notice that writing xy and yx is the same, because partial differentiating the partial derivative with respect to y with respect to x. So this is going to get really confusing, so I'll write it down. So if you have the partial derivative with respect to x of the partial derivative with respect to y of f, that is equal to the partial derivative with respect to y of the partial derivative with respect to x of f, as long as f is continuous. So obviously f has to be continuous, because if it's not continuous we can't really take a partial derivative a directional derivative of it. So as long as f is continuous, this holds. So we can actually switch this order and make it into xy over here, so that these two terms are the same. And now we get, so cos and cos become cos square theta times f sub x square. So x square is actually xx, but I'm writing it as x square so that it's a bit shorter. And then you will have sine times sine, so you'll have sine square theta f sub y square of xy, and plus, and then we'll have cos times sine, so you'll have cos theta sine theta, and you'll also have sine cos over here, so that's 2 cos theta sine theta f sub xy of xy. And this is the second partial directional derivative of our function. And now you may notice a pattern. So what we are doing here is basically for every x we are removing a cos, and for every y we are removing a sine. We are also having the binomial coefficients as the coefficients over here, because if you see what is 1, well, we have 1 over here, so 1 is just 2c0, and then we have 1 over here as well, so that is just 2c2, and we have 2 over here which is actually 2c1. So I should have written this term over here, but I hope that doesn't confuse you. So you have the binomial coefficients, and this, and using this information we can actually make a hypothesis. So just like in the kth derivative of a single variable function, we made a hypothesis that the kth derivative actually is equal to a certain summation, and then we proved that hypothesis using PMI. So we are going to be doing the same thing over here. So what is the hypothesis? So the hypothesis is that if you have the kth directional derivative of f of xy, then that is in fact equal to the sum as r goes from 0 to k of cos theta to the power r, sin theta to the power k minus r, and f sub x to the r, y to the k minus r, x, y times kcr. So this is our hypothesis. So I'll just write h over here, hy, because this is our hypothesis. So now where does this hypothesis come from? Well, the hypothesis comes from the fact that the coefficient of cos theta and sin theta always add up to k, because here you have cos square, so the overall exponent is 2. Here you have sin square, so overall exponent is 2. And here you have cos sin, so cos to the 1, sin to the 1, so 1 plus 1 is 2, so overall coefficient is 2. And kcr is this binomial coefficient. And similarly, just like in cos theta sin theta, you also have the exponent of x and y adding up to k. So here you have x square, y square, xy, 1 plus 1 is 2. So that is where this hypothesis comes from, and maybe I should draw a bracket over here because kcr is in the next line. So we're summing all of this basically. And we also notice that for every x in the subscript, we get a cos theta multiplied, and similarly for every y in the subscript, we get a sin theta multiplied. So that's why for the coefficient of x and the coefficient of cos theta are the same for y and sin theta. So this is our hypothesis, and now we are going to be doing a proof using induction. So we have already proved this for k equal to 1. You can check for yourself. So I'll remove this and I'll just let our glorious formula be there. And for k equal to 1, you can check for yourself that this summation is actually the same as this. I won't be doing it, it's fairly trivial. You can check it for yourself if you don't believe me. So now we want to prove that assuming that this is true, the partial derivative, the directional derivative, k plus 1th directional derivative of f of xy is equal to the sum as r goes from 0 to k plus 1 instead of k. So basically you replace k with k plus 1, and you will have cos theta to the r, sin theta to the k plus 1 minus r, f sub x to the r, y to the k plus 1 minus r, xy times k plus 1 cr. So this is what we want to prove, because assuming our hypothesis is true using induction, if we prove that this is true, then we have proved that our hypothesis is true. So now to prove this, let's directional differentiate our hypothesis on both sides. So I'll get rid of this. Just keep this thing in your mind, at the back of your mind. Wherever you have k over here, you just replace it with k plus 1, and whatever we get, that's what we want to prove. So I'll get rid of this for now. And now let's directionally differentiate both sides. So as I said previously, this is just the directional derivative, the k plus 1th directional derivative of f of xy, and this is equal to, so as I said, the directional derivative of the sum is the sum of the directional derivative. So you can take this thing inside, and similarly you can ignore the cos theta, sin theta and kcr because they are constants. So you will have the sum as r goes from 0 to k of cos theta to the r, sin theta to the k minus r, directional derivative of f x to the r, y to the k minus r, xy, and into kcr. So this is what we get, and we want to prove that this is equal to, so if I call this entire thing p of k, for example, then we want to prove that this is equal to p of k plus 1. This is what we want to prove, but we haven't proved it. So this will be equal to the sum r goes from 0 to k. So now let's first differentiate with respect to x. So we'll have we'll increase the exponent of x by 1 and cos theta by 1. So we'll have cos theta to the r plus 1, and then sin theta remains the same, k minus r, and then we'll have f sub x r plus 1, y remains the same. So I'll not write the x comma y because we don't really need that, and then you'll have kcr, which also remains the same. And then to that we are going to be adding, so I'll write this in a bit better way, and then to this summation we add another summation. So r goes from 0 to k, and this time we are going to be differentiating with respect to y. So we'll increase the exponent of sin theta by 1 and the exponent of y by 1. So you'll have cos theta to okay, so now you may have the question in your head, how do we bring these two summations into one summation, because that's what we want to do ultimately. Well, there's a clever trick to do this, and I have showed that trick in the kth derivative of a single variable function video, and it is to change the index. So let's change this index and make it run from 1 to k. So we are changing the index from r to r plus 1. So this will become 0 will become 1, and k will become k plus 1, and then r plus 1 will become r, and k minus r will become k minus r minus 1, which is in fact k plus 1 minus r. So this will become, so I'll just rub it out and write it, k plus 1 minus r, and then once again r plus 1 will become r, and this will also become k plus 1 minus r, and then r will become r minus 1. So index changing, as I said in the previous video, is a bit confusing, so just go over all of the stuff that I just did in your head and see if it matches up with what you intuitively think. And now we are going to be using a nice property that kcr minus 1 plus kcr is equal to k plus 1 cr, and to see where this comes from, just go back to the kth derivative of a single variable function video. I've shown all of these tricks over there. So now to group these sums into one sum, we are going to be bringing them together. So I'll get rid of this stuff because we don't need it. Okay, so how exactly are we going to bring two sums into one sum? Well, first of all, notice that the indices of these two sums aren't the same. The index is running from 1 to k plus 1 here and 0 to k over here. but notice that the interval from 1 to k is in fact common. So if I draw the number line, 0 will lie over here, 1 will lie over here, let's say k lies over here, and k plus 1 will lie over here. So this summation is in fact going from 0 to k, and this summation is from 0 to k, and this summation is from 1 to k plus 1. So this interval from 1 to k is common between both of them. So we can use that fact, and we can separate out the k plus 1th term over here and the k 0th term over here. So we'll have the 0th term in this summation, which is cos theta to the power 0, so we can ignore that, and then sin theta to the power k plus 1 minus 0, so that's k plus 1, f sub x to the 0, so we can ignore that, and then y to the k plus 1 times k plus kc0. So kc0 is equal to k plus 1 c0, which is 1. So we can use that and just write k plus 1 c0 over here. And then we have to separate out the k plus 1th term from this summation, because that's also an odd one out. So you will have so here the exponent of cos theta will become k plus 1, and sin theta will become 0, and then here you will have k plus 1 in the exponent for x, and for y it will become 0, and then over here you will have kc k plus 1 minus 1, which is equal to 1. So that is also equal to k plus 1 c k plus 1, right? Because this is just k. So k c k is the same as k plus 1 c k plus 1. So we can write it like that. Doesn't really matter. And then, since we are grouping the two sums together, you will have the sum. Okay, so I've written down what we got so far, and I've clubbed the two summations together from 1 to k, and this is what we get. So cos theta to the r comes out common, sin theta to the k plus 1 minus r comes out common, f sub x to the r y to the k plus 1 minus r comes out common. The only thing that doesn't come out common is kcr minus 1 and kcr. So I've written down that, and we already saw that this is in fact k plus 1 cr. So we can put that in, and there is our summation. So if you still don't see it, let me group in these two terms as well. So if you put r is equal to if you put r is equal to 0, then you will get this, because if r is equal to 0, then cos theta's exponent is 0, so it will become 1. Sin theta's exponent will be k plus 1 minus 0, which is k plus 1. Here the exponent for x will become 0, for y it will be k plus 1. So here you have y to the k plus 1, and you will have k plus 1 c0, you have that over here. And if you put r is equal to k plus 1, then cos theta's exponent will be k plus 1, sin theta's will be 0, then for x it will be k plus 1, for y it will be 0, and you will have k plus 1 c k plus 1, which you have over here. So this is in fact the 0th term, and this is the k plus 1th term. So we'll have the sum as r goes from 0 to k plus 1 of blah blah blah. Et voila. We have proved our hypothesis, because if you remember, we called this thing, if you look at this will precisely be p of k plus 1, because of the way we defined p of k, and that proves our hypothesis using PMI. And that's it for this video. I hope you enjoyed this, and I hope this formula looks really a nice hybrid of the kth derivative of a single variable function and the directional derivative of a two variable function. And thanks for watching.
Turn up. Let's go.